The rise of atmospheric O2 was a milestone in the history of life. Here we summarise the major theories and evidence from geological literature that pertain to when and how O2 first accumulated in significant amounts in our atmosphere. When and how O2 first accumulated on the Earth remains a puzzle. Solving this requires an understanding not only of the biological capacity to produce and utilise oxygen first appeared, but also the chemical and physical processes that enable the fluctuated rise of O2 to its current level of 21% in the atmosphere.
Around 2.45 billion years ago, there was a puzzling increase in atmospheric O2. This occurrence is known as the Great Oxidation Event.
To understand the Great Oxidation Event, we first have to go back in time.
Previous to the GOE, Earth had low oxygen levels and high amounts of methane gas, causing higher global temperatures. There was a reducing atmosphere, and the subsequent lack of an ozone layer allowed dangerously high levels of UV radiation to reach the surface.
There were no leafy plants, no animals, and no insects. Although there was some bacterial life on land, it was the oceans that teemed with it, and even then it was much simpler than the complex multicellular life that it is today.
The discovery of mass-independent fractionated sulfur has proved the oxidation event a certainty and even provides a specific timeline for the release of free oxygen into the atmosphere. Isotopes are atoms of an element with different mass numbers due to different amounts of neutrons in the nucleus. Isotopes are usually fractionated according to their relative mass. This fractionation is termed mass-dependent fractionation. The photolysis of sulfur dioxide and sulfur monoxide by UV radiation results in sulfur isotope fractionation that is mass-independent. This independent fractionation process requires low amounts of oxygen in the atmosphere, sufficient amounts of reducing gases, and lots of sulfur and methane in the atmosphere. For these reasons, this fractionation process can be associated with an atmosphere like the one present before the Great Oxidation Event. Mass-independently fractionated sulfur isotopes give evidence for the Great Oxidation Event, as rocks older than 2.45 billion years show large amounts of independently fractionated sulfur, whereas rocks younger than 2.32 billion years show basically none. In the present-day atmosphere, mass-independently fractionated sulfur occurs on very small scales and is quickly homogeneized by the oxidizing atmosphere. This change in the atmosphere is preserved in sulfide and sulfate minerals in rocks, as they have contrasting isotopic compositions of reduced and oxidized sulfur. While these isotopes prove there was a dramatic change in the atmosphere, they do not give insight into the actual causes behind the Great Oxidation Event.
We will now look at the possible causes for the GOE.
A popular idea for the rise in O2 was the appearance of photosynthetic organisms such as cyanobacteria. These are microscopic organisms that can only be seen under the microscope. The cyanobacteria dominated the premortal seas, forming extensive stromatolite reefs and releasing increasing amounts of oxygen into the atmosphere. A stromatolite is a solid structure created by the cyanobacteria. The cyanobacteria form colonies and trap sediment with their sticky surface coatings. The trapped sediment then reacts to calcium carbonate in the water to form limestone. Stromatolites look very much like a rock, but unlike rocks, they are actually alive. Each stromatolite has a top surface layer teeming with living, active cyanobacteria. These photosynthesizing organisms produce oxygen by taking in CO2 gases from the atmosphere and releasing O2 as a waste product. Recent research examining ancient rock deposits suggests that oxygen existed in the atmosphere up to 3 billion years ago. This would mean that photosynthesizing organisms evolved long before the Great Oxidation Event occurred, sometime during the Archean. So, if photosynthetic life rose that early on Earth, why didn't oxygen suffuse the atmosphere until much later? Past studies have suggested potential explanations for this, including that photosynthesis may have been an inefficient process. There may have been a lack of key nutrients needed for the microbes to grow, or else oxygen may have been poisonous to the microbes that produced it in the first place.
Another possible cause for this puzzle is submarine volcanoes.
It's not just biological processes that has an effect on oxygen production. Physical and chemical processes also contribute to oxygen levels. Another theory is that there was a change in the oxygen sinks. Prior to the GOE, the predominant sink for oxygen in the Archean era was submarine volcanic eruptions. These submarine eruptions released large amounts of reduced iron into the oceans. The released iron reacted with the oxygen, causing there to be a rusting of the oceans, giving them a reddish colour.
Banded iron formations are widespread in the Archean. The deposition of these iron formations are linked to high volcanic activity events where iron is released hydrothermally in ocean basins with layers of silica, and their presence is assumed as evidence for anoxic oceans during the Archean.
The mixture of gases and lavas produced by submarine volcanoes scrubbed oxygen from the atmosphere and bound it to oxygen-containing minerals. Therefore, as long as the reducing ability of submarine volcanoes was greater than the amount of oxygen created, the atmosphere had no oxygen. This leads to another puzzle. If submarine volcanic activity was constantly removing the oxygen from the atmosphere, what changed that led to the sudden rise in the O2 levels 2.5 billion years ago? A noteworthy event that occurred at the same time as Great Oxidation Event was Earth's tectonic evolution, which formed a large portion of continental crust while global ocean volume was decreasing. As a result, the area of crust exposed to the atmosphere increased significantly, causing the formation of subaerial volcanoes. The shift from submarine volcanoes to a mix of subaerial and submarine volcanoes, more similar to that observed today, would have reduced the overall sink for oxygen and led to an increase of atmospheric oxygen. The increase in O2 occurred because the redox state of volcanic gases differs between subaerial and submarine. Submarine volcanoes erupt at lower temperatures and thus produce more reducing gases, which in turn use up the oxygen. Volcanic gases that erupt subaerially are generally stable at high temperatures and low pressures. Consequently, oxide gases dominate, allowing for a more oxidizing atmosphere and as a result higher levels of oxygen.
Now we can put all the pieces of the puzzle together.
Even though there is evidence for cyanobacteria producing O2 since the early Archean, it is apparent that oxygen sinks were greater than oxygen production.
It wasn't until the appearance of subaerial volcanoes that oxygen began to diffuse the atmosphere.
This triggered the Great Oxidation Event and subsequently led to the atmosphere we know today.
Even though it is apparent
Submarine eruptions.
Should I close open book?
there's evidence for O2 releasing blah 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 into the atmosphere, something about sinks.
Process. The elements of the...
I forgot this.